All right, good afternoon, everyone. Hope you had a good little break. All right, so what are we doing? We are in our last week of lecture before the final, which is next week. So just as a reminder, we have just our last class meetings here are going to be today and then on Thursday. And then remember, no class on Tuesday. All right. And then our final is going to be on December 9th, next Thursday. We will be here at 12:30, which is 30 minutes earlier than normal. That's not my doing, that this has been the plan. This is the way they do finals. 1 o'clock finals that are our 40-minute classes always start at 1:30 or 12:30. So we'll go from 12:30 to 3:15. I did send out earlier a review.
Yeah.
One, maybe two. Did I send two?
Yeah, it looked like two separate views.
Two separate reviews. So take a look at those. I know you're going to be asking me for solutions. Maybe for one of them, I'll give you solutions. I don't know if I'll give them for both, but that's something for you to start working on, at least over the next, until we meet again on Thursday. Okay, 100, yes?
Yes, so it was 12 o'clock on Tuesday the 9th?
No, 12:30 on Thursday the 9th.
Yeah, Thursday the 9th.
Yeah, Thursday the 9th, 12:30. And we'll come in here and we'll do what we normally have done, right? Everyone will have their camera set up and all that. I'll send you the exam and all, all that fun stuff, so. Okay, so I know that you all have questions about the optimization problems. I know that those are tricky, right? They can be messy, and that there's really no like cookie cutter template that you can do for each problem is a little bit different. So I have had several students ask me about problem number 23. So right before class, I was with one of your classmates and we went through the whole problem and I recorded it. And so I'm going to post that later on. I'll post it with today's lecture. It'll be a separate video, but it'll be in there. So you can see me work through number 23. Here's the work, but I'll have a video for it later. So if you have questions about optimization, let me try and get through today's material. And then once we get through today's material, we can, if there's time, we will do, maybe if you have another optimization problem you want me to look at, okay? I've also been asked about extra credit bonus or whatever. There are kind of two major bonuses in this class. That one is, have you had your camera on throughout the semester, right? That was number one. Number two is, have you kept all your homework in a folder, binder, spiral for the whole semester, all the homework you've been doing? So those are the two main things. So for the binder of homework, you just need to make sure you have that with you at the final. And so what I'll do, I might even do it on Thursday. So bring it on Thursday also. It's just going to be like, how many you show me your pages before the test? You're going to basically do that. So it'll take a few minutes because everyone's got to kind of flip through. And I'm not looking for like every single problem on every homework assignment that you did, but you should have a pretty fat notebook of homework by now. So
mine's almost filled, actually.
Yeah, you should have a lot. All right, so bring that Thursday and then remind me if I forget, because I'll start wanting to talk about things. And if I forget, remind me, and then I'll need probably 5-10 minutes to do that. All right.
Sure. Quick question.
Yes.
So I do everything on a tablet.
Yes.
Would I be able to have that on the exam, or I guess I should just print it off, right?
You mean to show it to me? Don't print it. Don't print it. What kind of files do you have?
It's on OneNote, so they're
OneNote?
all like. So
Okay.
I'll show you.
Yeah. You know what? I mean, we could do it real easy. I mean, you could like save the notebook and like I can let you upload it or something if you wanted to.
Yeah, I could probably do that then. It'd be easier.
Yeah. Okay. All right. So today what we're going to do is we're going to start talking about antiderivatives. all right? And we're gonna see how far we can get with antiderivatives. And this is kind of, we're just putting our toes into the water here for Cal 2, all right? But this is something we're supposed to talk about in Cal 1. So it's not like I'm getting ahead. This is supposed to be covered in Cal 1, but I'm just letting you know, this is a transition point where you go from Cal 1 to Cal 2 as far as is the technique of what we're trying to accomplish. Everything we've done in Cal 1 has pretty much been based on the taking a derivative of a function. And so now what we're going to do is talk about this thing called antiderivative, and it's a pretty simple concept. It's a really simple concept. So when you talk about an antiderivative, let me just motivate it before I give you the definition and all that. Let me just tell you, let's say that we have a function and I tell you that its derivative is 2x, okay? And then I ask you to find what the function was, right? Find f. So I'm saying there's the derivative, right? Tell me what the function was. I would
It's x
feel
squared.
everyone feel comfortable with that idea that it had to be x squared. F of x equals x squared, right? Is that pretty straightforward? Because you feel comfortable with the idea of, oh, you recognize that, right? Oh, that's a derivative of x squared. Now, is that the only answer? Is there another answer that would have worked?
You could do 2x with some just number added on, like +2 or -7 or something like that.
Okay, you could have done the x squared, right, with some number added on. You could have said +2. That still would have worked because the
guess-
derivative of that would have still been 2x because the derivative of the constant would have gone away, right?
Any constant could be there at the end, couldn't it?
Any constant, right? I could actually have, -7. Anything you want to come up with, it doesn't matter, right? X squared, I could say plus pi if I felt like having fun, right? It doesn't matter if I add or subtract a constant, right? If I add or subtract a constant, I'm still going to be correct, won't I? So all of these are answers, right? So how many answers are there?
There'd be infinite answers.
There's an infinite number of them, right? There's an infinite number of answers to this. There's infinite functions, right? There's an infinite number of functions that would satisfy this relationship, that when you take the derivative of it, you get 2x. So since there's an infinite number of them, we want to come up with a way to give an answer that represents all of those answers, all of those infinite solutions. So we would write something like this: f of x equals x squared plus any constant, capital C. This capital C can be any real number, positive or negative, all right? So you're adding either a positive number like 2, or you're adding -7, which is same as -7. So this covers all of them, right? This is our, what we call our general antiderivative. Of 2x, all right? This would be the general antiderivative of 2x. Now, let's just try something a little different. How about this example? What if I told you the derivative of some function is not 2x, but just x? So now you have to think about this a little bit, right? You know, first of all, well, hopefully you know this, that whatever the function is, the power on it has to be squared. Do you agree? Because when you take the derivative, the power's got to come down and become the x to the first power, right? So we know it's got to be x squared. Yes?
Would be 1/2 x squared.
1/2. So you need to somehow kill off the 2 that's going to come out, right? When you do this power rule, when you take derivative of this, that 2 is going to come out, and you don't want that 2 here. You want it to be gone. So what you're going to do is put a 1/2 in front of it. And that will kill the 2 off when I say kill it, it won't like make it turn into 0. It just turns into a 1, right? You do the 1/2 times the 2 that comes out, it becomes a 1, and now you've got the x. Now you still need plus c, right? That covers all the possible answers. Let's do another one. All right, let's go around. I'm going to go call on people today. Well, everyone's got their cameras on today. All right, so how about, let me bring up my list of everyone. I'll just go down the list. So how about Angel? What do you think?
I think the fx is going to be x to the third plus c.
There you go, x to the third plus c. Hey, here's the good news, everyone. You can check your answer, right? I mean, all you have to do is take derivative, and if it matches up with that thing on the left, you got it, right? You got it. Okay, let's do another one. Let's see, Anna Marie. How about if I didn't have Anna Marie? How about if I didn't have the 3 out there? So just x squared.
Wouldn't that just be 1/2 x plus c?
1/2.
Wait, 1/2 x squared plus c.
We're starting with x squared. So the antiderivative
be
would have one power higher, wouldn't it, Anna Marie? Right,
Wouldn't
so
it be 1/3 x cubed plus c?
yes,
Oh,
One-
okay, that makes
you
sense.
see?
Yeah.
So because it was squared, you know that the original function has to be x cubed, right? And then when you do the derivative, you know the 3 is going to come out, but you want to kill it off. So you put a 1/3 out here. That makes sense, everyone? How about this?
Yep.
Let's see, Arturo, you're up. All right, Arturo, what do you think? What about the power on x? What does the power on x have to be?
It's going to be x to the third.
Okay, it's got to be x to the third, right? When you take derivative of that, Arturo, you need it to turn into a 4. So any ideas on how you can do that? A 3 is going to come out,
4/3.
right? A 3 is going to come out. You got, say it again?
4/3
That's
x
it,
cubed.
4/3. 4/3 has to be here. Exactly. So when that 3 comes out, it cancels with this 3 and you've got the 4 there, right? You make the 4 match. Make sense, everyone? Plus c. Let's not forget the plus c. Here's another way you could do this. Do you remember when well, you should remember, when we take a derivative, constants come for the ride, don't they? They come for the ride. So when you do antiderivatives, it's the same thing. Constants come for the ride. So if I want to try and find an antiderivative, what I can do is say, oh, look, I've got a constant here, right? Let me ignore it for a second. What's the antiderivative of x squared? Well, I know that that's 1/3 x cubed, okay? I know that, right? And then I say, but wait a minute, I had that 4 here. So I need to tack the 4 onto the front and then say plus c. And now when the 3 comes out, it'll cancel with the 1/3 and you'll have the 4. Does that make sense? 2 different ways of doing it, but you get the same result. You put these 2 numbers together, you get your 4/3. Try another one. What if I tell you the derivative of some function is, let's do this, -3 x plus 5. Okay, Bethany's up. So Bethany gets, I guess, a harder problem because I have 2 terms, don't I, everyone? So what do you think? When we take a derivative and we have addition, subtraction, we do the derivatives individually, right? Do you think it works the same way trying to find the antiderivative? Yes, it does. Okay, that's good. So Bethany, if you're here, can you do one of these?
Well, I know the 5 would be 5x.
Okay, good. So the 5 would be 5x. Everyone follow that? The antiderivative of 5 would have to be 5x. Good. While we're here, can we just throw the plus c, Bethany? Just throw it
Yes.
on there. We're going to have a plus c on every antiderivative. For the rest of your life, all antiderivatives are going to have plus c's. Okay. All right. So Bethany, now look at that first one, negative 3x. I want you to ignore the negative 3 for right now. And just focus your attention on the x. What would the antiderivative of that have to be?
X squared.
Okay. Now, when you do that, the 2 is going to come out. You don't want that 2, right? Because you don't have a 2 here. So what are you going to need in front of it?
1/2.
1/2. Okay. And now, Bethany, I want you to bring your constant and slap it right in front. Okay. And that's multiplication. And then just put those two numbers together. Negative 3 times 1/2 is negative 3 over 2. X squared plus 5x plus c, and we're done. Bethany, does that make sense?
Yes.
Everyone else, we good?
A question.
Makes sense to me.
Can we do this on a regular function instead of like a derivative?
Say again?
Can we do this on a regular function instead of a derivative? So,
Yeah,
like,
yeah, absolutely. Right now, I'm just trying to make the relationship from what we're familiar with, which is
Okay,
if I gave you the derivative, can you tell me what function it came from, right?
yes, yeah.
Okay. All right, let's do another one. How about this? I tell you that the derivative of some function is square root of x plus cube root of x plus 4th root of x. All right, now things are starting to get messy. Things are starting to get messy. So what is the antiderivative? So what function did this come from? Well, here's one thing you know for sure. Plus c, right? You got that much, right? That's guaranteed. But the rest of this is uglier because we've got these roots now, right? So it might help us if we rewrite these. This is x to the 1/2 power. This is x to the 3rd power. And this is x to the 4th power. 1/4, sorry, 1/3, 1/4. 1/2, 1/3, 1/4. And so we're trying to figure out where does this come from, right? Like where does this, what do we take the derivative of to get these? So this is not as easy to process mentally, all right? It's not as easy to process. So because it's not as easy to process, what we're gonna do is we're just gonna put this on hold for a moment, all right? And I want us to think about this in a general sense right now. What we've done. If I give you the derivative of some function is x to some power n. Let's discuss the antiderivative. The antiderivative, can you tell me what the power on this x has to be?
In plus 1.
It's one more than n, right? No matter what, it's got to be 1 power higher because we know when we take the derivative, the power is going to be subtracted by 1, right? So if this power is n, I know that this has to be n plus 1. Right? I know that for sure. But now I have a problem because when I take the derivative of this, the n plus 1 is going to come out, isn't it? And I don't want it there. I want to get rid of it. So how do I get rid of it? Like if this was a 3, I would put 1/3, right? If this was a 2, I would put 1/2. If this was a 5, I'd put 1/5, right? So why don't I put a 1 over n plus 1 right here? And now when the n plus 1 comes out, it'll cancel the n plus 1, right? That will automatically kill it. Y'all get that? And then plus c. This is a formula, okay? This is called the power rule for antiderivatives. Not for differentiation, but for antiderivatives. Let's just show that it works real quick on a previous example we did. When we did the derivative earlier was x squared. That means that n here is 2, right? N is 2. Let's use this formula without even thinking. Let's just plug 2 in for n here, and we get 1 over 2 plus 1 x to the 2 plus 1 plus c. Right? That's what would happen. And this gives me 1/3 x cubed plus c, which was the answer, right? So this is a kind of like, you don't need to think about it. You just need to figure out what n is, plug it into the formula, you're done. I didn't want to give you the formula right off the bat. I wanted us to think about why it's this formula. There's a reason. So this formula is very important. All right. This formula is very important. There's one problem with this formula though. One problem. This formula works if n is not -1. What if n is -1? Look at what happens. If you try and plug -1 in right here, what happens? -1 plus 1? 0.
We get division by
Division
0.
by 0, right? So this formula does not work if n is -1. Y'all see that? Everywhere else it works, but not when n is -1. So that seems to be like a special case. So what would happen if n is -1? Then what does this look like? The derivative is actually what? X to the -1. Do y'all recognize that? 1 over x. That's what that is.
Yeah.
Can you think about what you take the derivative of to get that?
Natural log of x.
Natural log of x. So we actually do know the antiderivative of this. The antiderivative of this is the natural log of x plus c, okay? Plus c. So let me just take a step back. If we're given a power function, x to the n, and we want to know the antiderivative, we can use this formula to find the antiderivative as long as n is not -1. If n is -1, then the answer is just natural log of x. Right? So we've got all powers of x covered now. Understand? All powers of x are covered. Now I'll restate this later. Okay, these two together make up everything we need, right? This is if n is -1, this is if n is not. So let's go back to that problem right here, and let's see if we can do this now. So I have 3 separate things, right? Addition between each of these, 3 of them individually. Each of them has a different power, 1/2, 1/3, and 1/4. So I'm going to do the power rule on each one of those. So let me try and find this antiderivative. All right. So n here is 1/2. Who's up? Daniel Patterson is up. So Daniel, for this first one, right? N is 1/2, right? So go ahead and let's crank out. I'll bring this. Oh, do you need it? Did you write it down? Should I bring it?
Yeah, I wrote it down.
You wrote it down. I'll bring it down here for everyone so they can see it. Here's the formula. So go ahead, just tell me, don't simplify anything. Just tell me, just plug in and tell me what I write here.
1 over 1/2 plus 1 times x to the 1/2 plus 1th power plus c.
Plus c, right? Good. I agree. Now, this one's going to have a plus c in it, right? This one's going to have a plus c. This one's going to have a plus c. They're all going to have a plus c, right? So what I'm going to do is at the very end, I'm going to just do a plus c at the very end. Do you want to keep going, Daniel? You want to do the next one? Because we have addition, we can do plus and then move to the next one.
Yeah, then it'd be 1/1/3 plus 1 times x raised to the 1/3 plus 1.
And then plus C. Okay, good. I think we've got, oh, y'all remember Daniel, the other Daniel. You want to do the last one here?
Yes, sir.
Go ahead.
1/1/4 plus 1 x to the 1/4 plus 1.
Plus 1. And now we get the plus C, right? Now the plus C. All right. So you're going to be doing a lot of adding ones to things in antiderivatives. Okay. There's a lot of this adding one, add one, add one, add one, add one, add one, add one to these fractions, which means you got to get kind of fast at adding these things up. So I'm not going to do all of these in this detail, but when I do 1/2 plus 1, right, what I'm doing here, 1/2 plus 1, I'm just getting a common denominator. So I turn the 1 into 2/2. And then when I add them, I add across the top and I get 3/2, right? So my next line should be 1/3/2 x to the 3/2. Okay, that's 1/3/2 x to 3/2 plus, now this one I'm not going to show the detail. What's 1/3 plus 1?
4/3.
4/3. So we get 1/4 x to the 4/3. Then plus 1/, it should be 5/4, because you're taking 1/4 and adding 4/4. That's 5/4. X to the 5/4, and then plus C. And there's one more thing I'm going to do. This 1/fraction, 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 those are just the reciprocals, right? So I can write this as 2/3 x to the 3/2 plus 3/4 x to the 4/3. Yeah, plus 4/5 x to the 5/4 plus C. There we go. That's your antiderivative. You could check your answer, couldn't you? You
Yeah.
could check your answer. You could take the derivative, and if you take the derivative, you better get back this. All right, which you should, right? If I ask you to take derivative, let's just check the first one. You'd bring the 3/2 off or out, it would cancel with the 2/3 right away and just become a 1. And then you'd subtract 1 from 3/2. 3/2 take away 1 is 1/2. So you get x to the 1/2. Understand? What do y'all think
Yep.
so far?
They seem interesting. They aren't too challenging though. I'm
Yeah, with
excited
the
for
power
whatever's
rule,
gonna
it's
make
not
them.
that, it's not terribly bad. All right,
Yeah,
let's do another
I'm
one.
excited for quotient rule. That's what I'm most excited for.
Oh, yeah, there is none, no. That's the problem. There's no way to undo a quotient. So
Oh,
how about this one?
well, that would do it.
Yeah, it's what's gonna make Cal too hard. Okay, so now let's do this same thing, but I want you to look at their reciprocals instead. It's the same problem I just did, but instead of square root of x, cube root of x, fourth root of x, it's 1/square root of x, 1/cube root of x. So right now, the only thing we know how to do, the only antiderivative we know is if we have x to a power, right? That's it, x to a power. So before you do anything, you've got to make all of these look like x to powers.
It'll be the same as the last one, except they're all negatives. All
All negative powers, yeah. So we can rewrite this, okay? Rewrite this as 1/x to the 1/2 plus 1/x to the 3rd. This thing is driving me crazy. Plus 1/x to the 4th. Okay, that's the original, the derivative we're looking at. And now before I do power rule, I bring all of those up. Now I'm ready. Okay, now I'm ready. Why don't you take a minute or two to apply that, excuse me, to apply this formula to those three. And clean it up as much as you can, and then I'll call on someone. I've got Emily, Ethan, and Hunter are the three that are in line here. So I'll ask each of you, Emily for the first part, Ethan for the second, Hunter for the last one. We'll do them separately. I'll give you a few minutes. So at the end of Cal 2, by the time you're finishing Cal 2, everyone in this class would be done with this problem already, right? Like it would be, you would do it in your head. Like this wouldn't be something you're writing anything down. You just go straight to the answer. I'm trying to give you an idea of like what you need to be able to do mentally by the time you get through Cal 2. This would all be done without really writing anything, but it takes time to get there. I'm just telling you.
Hey, as long as there aren't too many related rates in Cal 2, I'll be fine.
Yeah, they're not. Ethan, you look like you're done. Yes. Hunter, you look like you're done. You want to give me, how about Ethan, you give me the second part, Ethan. Emily, I'm not calling you because you look like you're still writing, so.
Three
Oh, wait,
halves.
are you just doing like, are we just doing like one of them?
Well, I was gonna call on, Emily, I was gonna call on you just to give me the antiderivative of that first one.
Oh, okay. I thought you meant like to find everything. Okay.
No.
Oh, okay. So then it's like 1 over -1/2 plus 1x, like to -1/2 plus 1. Okay, sorry. I thought you meant
Oh,
like
that's okay.
to find all of them. So I was like trying to find all of them and then find the answer, but okay.
Yeah, you got that part right. Did you simplify this yet, Emily, or no?
Yeah, I simplified it. So
Okay, what did this turn into?
I got 1 over 1/2 x to 1/2, but I guess if you wanted to, you can make it 2x 1/2.
We do want to do that, yes. 2x to the half. Perfect. Yep, that's right. And then, let's see, Ethan, you got the second part?
3 halves, x to 2/3.
So plus 3/2 x to the 2/3. And then Hunter, what'd you get for the last part?
4/3 x to the 3/4
4/3
plus
x
c.
3/4 plus c. That looks good to me.
These are some spicy problems.
Yeah. So let me tell you how I do it, okay? Just so you can start to build to the point where you're not writing all this down. And it's going to take time for you to get comfortable. So what I do is this. I take this number, I add 1 to it. Okay, so I take -1/2 plus 1. I do that mentally. And I get 1/2. So I write that down, x to the half. Okay. And then out front, I put the reciprocal. The reciprocal of 1/2 is 2. So I put that out here. Understand? Let me do the next one. Okay, I take -1/3, I add 1 to it. -1/3 plus 3/3 is 2/3. So I'm going to write x to the 2/3, and then in front of it, I put the reciprocal, 3/2. Done. That's how you do the power rule. right? Last one, -1/4, I add 1, that's going to give me 3/4, x to the 3/4, and then I multiply by the reciprocal out front, 4/3. Okay. Now, I wanted to talk about this. Let's look at just this one right here, just that one, just for a second, right here, all right? I'm going to write something down and you tell me what you think of this. I'm going to claim that the antiderivative of this is x over, let's see, that's x to the 1/2. Didn't we do that earlier? What was the antiderivative of x to the 1/2? It was 2/3 x to the 3/2. 2/3 x to the 3/2. Okay, so what did I do here? I took this and I'm saying that this maybe is the antiderivative. I don't know. What did I do though? Can you tell what I did? How did I get x up here? What did I do to get x?
Oh.
What did I do? Can you all tell what I did or no?
You reciprocated something?
You took the derivative of the top and the derivative of the bottom.
Antiderivative. All I did is I took the antiderivative of 1 and put it here. Okay. And then I took the antiderivative of this and put it there. And my question is that allowed? Is it right? And the answer is no, it's absolutely terribly wrong. This is not correct. Okay. You can check it. You can check it. You can clean this up and take the derivative of it. You're not going to get this. And the reason it's not correct is because you're assuming that when you take the antiderivative of a quotient, that you just do the antiderivative of the top and bottom separately. But that's not how we took derivatives of quotients, right? The derivative of a quotient was a quotient rule, which was terrible. F prime g minus g prime f all over g squared. So reversing a quotient is not simple. So that's why we had to take each of these and rewrite them as powers of x and then use the power rule. Then we could do something. Very important. So let me do one more example. One more. Let's say we have the derivative of some function is equal to 1 plus 3 square roots of x minus 5 7th roots of x plus x squared all over x. And I want you to find f of x. So when you look at this, you see a quotient. You are not allowed to just do the top and bottom, do their antiderivatives on their own. You can't do that, all right? Your only hope at this point is to be able to rewrite this as x to powers. That's it. And you can't have a quotient like this anymore. But because of the way I presented the problem, I have a single term in the denominator, right? And I have multiple terms in the numerator. So I can split this up. I can take the original thing over here and do 1 over x plus 3 root x over x minus 5 7th roots of x over x plus x squared over x. I got lucky that I can do that because I have a single term in the denominator. And now I'm going to start thinking about how I could do the antiderivative of each of these. So when I look at this, I notice right away, this is that special case, isn't it? 1 over x is that special case where you had this one, right? 1 over x, the antiderivative is natural log of x. So I need to recognize that. So I'm going to put a little check here. I know how to handle that, okay? I know how to handle that. This one, I need that to be x to a power. And right now it's, you know, stuff on top and bottom. I can combine those together though. I can start rewriting this, you know, 3x to the half over x. And then this one I can write as 5x to the 1/7 over x. And then this one, well, x squared over x is just x. So now when I look at it, I know how to do that. I actually know how to do the antiderivative of that too. Well, I'll do power rule on that. I really just need one more thing, and that's to put these together and put these together. I have not done any calculus at this point. Everything here is just algebra, right? I'm just cleaning it up, you know, just manipulating it, massaging it, making it look the way I want it to look. 1 over x. Okay, this is going to be, you have to remember how to do this, right? X to the half over x to the 1 is x to the half minus 1, which is going to be x to the negative 1/2. So you need to know the properties of exponents. So this becomes 3x to the negative 1/2, and then minus 5. And then here, same thing, right? X to the 1/7 over x to the 1 is x to the 1/7 minus 1/7 minus 1, which is x to the negative 6/7. So x to the negative 6/7 and then plus x. Now I'm ready. Questions on that?
I got one
Now
for
I'm
the
ready.
end.
I'm sorry?
I got one, but I think I should wait until we finish the problem before I ask it.
Okay. So now I'm going to start taking antiderivatives. So I'm going to do this one first. The antiderivative of 1 over x is the special one. I know that's natural log x. Plus, now watch this. I have this 3 here. It's going to come for the ride. Okay. I'll clean it up on the next step. Now I'm going to do that thing I did on the last one. I'm going to take negative 1/2. That's my power. I'm going to add 1 to it. So negative 1/2, add 1. Negative 1/2, add 1. That's same as negative 1/2, adding, that's terrible, 2 over 2. Let me erase that shit. Okay. Right. So we're doing negative 1/2 plus 1 is negative 1/2 plus 2 over 2, which is going to be a half. Okay. So I know that my answer is going to have x to the half. Right. And what do I put in front of that?
2.
2, the reciprocal of 1/2. So I put a 2 there. It's going to join up with that 3. All right.
So 6x to the half.
It'll be 6x to the half on the next line. Okay, next one, I bring the minus 5 for the ride. And now I'm going to play that same game with the negative 6/7. I'm going to add 1 to it. So what's negative 6/7 plus 1? 1/7?
1/7.
1/7. So I'm going to have x to the 1/7. And out front, I'm going to put the reciprocal of that, 7. And then my last one is plus. Now this one, I could do the power rule, but this one you should just, it should be automatic at some point soon. The antiderivative of x is 1/2 x squared. And then plus c. And then clean up, make this a 6, make that a 35 with a minus in front, and you're done. Y'all good? Y'all good? Question, Hunter,
Yeah.
did we address your
Yeah.
question?
I was going to ask, and it might be answered on the next one, to be honest. What would we have done if we couldn't have split it up into those 4 separate things?
Yeah, okay, so let's imagine that this problem would have been instead of this, okay? Instead of this, what if this problem would have been let's say on the bottom, x plus x squared. Okay. I'll tell you right now that even my Cal 2 students that have finished the semester pretty much wouldn't be able to do this. It would be that difficult.
That's just what the quotients, the quotient like this, they're just that much awful.
Yep. That it's just that bad. Yep.
Yeah.
Just one little slight tweak to this and it's all over.
Yeah, because you basically, if I'm guessing correct, you need to look and see, okay, well, there's your subtraction. So those are your 2 halves. So then we need to find.
Yeah, it's too much to process.
That's a lot.
Undoing the quotient rule and product rule is very challenging. So in Cal 1, we have rules, right? We have the power rule, and we have the product rule, and we have the quotient rule, and then we have the big chain rule, right? Those are like those are the rules, and that's it. Once you learn those rules, you're in business. Like if you got those rules down, you can differentiate just about anything you can think of. As long as you break it down into its pieces, you can do differentiation. It's very mechanical. Antiderivatives, at least right now, they seem somewhat mechanical too, because I've given you a formula, but I'm here to tell you, like, for sure, it will stop being mechanical. And there won't be like, oh, this, here are the things. Oh, once you've got those down, you can find the antiderivative of anything. It just doesn't work that way. We come up with these techniques that we try, but they don't always work. And not only do they not always work, you're not quite sure sometimes which technique to use. So I don't want to get ahead of ourselves. Let's keep ourselves here. But right now, what we're doing is we're looking at only things we can handle. This isn't one of them.
So here's a question, just because it does kind of spur off that. Is it possible for there to be one like this where there just isn't an answer? It cannot be taken. The antiderivative, like the
Yes.
antiderivative, does not exist.
Yes.
Okay.
Yes. So it actually turns out that if you were to take all the functions that exist out there and throw them into a pot and close your eyes and reach in and grab one, the probability that you can find its antiderivative is essentially zero. Now, that may seem terrible, but it turns out in chapter 8, which is late into Cal 2, we developed something called series, specifically Taylor and Maclaurin series, which allow us to be able to do anything, really, find the antiderivative of anything within a certain precision. So there's always going to be a little bit of error, but the error is within our control. So in the real world, it's okay because you can only build things within a certain precision. So we have to wave our hands at some point and say, okay, we can't do a lot of antiderivatives, but then series will save us at the end, which is why series are so important. Okay. All right. I think it's definition time. All right. So antiderivatives. So first of all, we're going to change some of our notation. What I've been doing thus far is I've been giving you this, right? I've been giving you this. This has been given to you. And then what I've asked you to do is find this, right? That's what I've been doing. We're going to change the notation up now. Instead of me giving you the derivative of the function and notating it that way, I'm going to call this, change my little, where are you? There you are. I'm going to call this now f of x, some function, all right? And then I'm going to ask you for its antiderivative. So I need a way of telling you, like I'm talking about the antiderivative of that. So I can't use f of x, I'm already using it. So I'm going to use capital F of x. And so now the capital F of x represents the antiderivative of little f of x. So it's just notation. That's all it is. I give you a function now, f of x, and I ask you for capital F of x, which means go find its antiderivative. All right. So this definition says a function capital F is called an antiderivative of little f on some interval I if the derivative of capital F of x is equal to little f of x. So in other words, if we take this and we take its derivative, we better get this. That's what makes it an antiderivative. Now we've already seen that if we find a capital F, right, if we are able to find an antiderivative, then we can always add a plus c onto the end. And that will be the most general antiderivative we can find. And keep note that here c is any constant. Go with me? So now, when we have this plus c, we said it's an infinite number of answers, right? There's actually an infinite number of answers. So when we started today, we went, oh, okay, look at this example here. We said, let's take a look at 2x. and we said, oh, x squared would be an answer, x squared plus 2, x squared minus 7. There's an infinite number of answers, but they're all parabolas, aren't they? All of these are parabolas. And when you look at what, graph them, right? If I were to take the function 2x, which is this red function, this x squared plus 3, the blue one, is a specific antiderivative of 2x, right? Because I can take the derivative of this and get 2x. I can also change the value of c, which means I can move this parabola up and down, and that is, all of those are still antiderivatives of 2x, right? They all are. So when you think about the general antiderivative, that plus c, what it actually is a family of functions. They're all parabolas. They're all x squared plus or minus numbers. So just move it up or down. It's all of them. And what they all have in common is something really cool. Watch. If you go to any of these functions and you look, pick some x value, pick some arbitrary x value, whatever it is, and then go look at the slope of the tangent line on any of those curves. Do you all see what they all have in common? Right. Those slopes are all parallel, aren't they?
Yeah, they all have the same derivative.
They have the same derivative, exactly. The same value of the derivative at any point. Doesn't matter where you go. You can move to any member of the family, and they all share the same slope of the tangent line. That's what makes them the antiderivatives of 2x. So that's just a visual representation of what we're doing here. We're finding this family of curves. I have another example here. This right here is the red function is a quadratic function, right? It's quadratic. The antiderivative is this blue function, which is this cubic function. I can move it up and down and create the family. And all those family members, again, have the same sort of idea of the derivative, no matter where I go. Come on. Oh, my computer's not liking that. No matter where I go on any of those family members, they all share the same slope of the tangent line. All right. All right, let's move on. We're going to do more antiderivatives now. Okay, how about this? New notation now. Little f of x equals cosine of x. Find capital F. All right, and let's see who's up here. Isabella, you're up. So I haven't given you any of this. I want you to just think about this, Isabella. Can you think of what function you take the derivative of to get that?
Negative sine of x.
Okay. I'm going to write it down, and then I want you to think about it. If I write negative sine of x here, what would the derivative of this be? So what's the derivative of sine?
Cosine.
Cosine, and that's what this is, right?
Mm-hmm.
So you actually don't need this negative, do you?
Oh,
See
I
what I'm
guess
saying?
not.
Like, you don't need this negative, because if I take the derivative of sine, don't I just get cosine?
Yeah.
Yeah. Does everyone see that? Plus c.
Plus
Be my plus c. So Isabella, the antiderivative of cosine of x, the antiderivative is just sine. Why? Because the derivative of sine is cosine. You'll follow? Everyone follow? Everything's backwards, so we have to be careful here. How about this one? Jackson, you're up. How about sine of x then, Jackson? Be careful with this. If little f of x is sine x, I want you to find me the antiderivative. So what do you think, Jackson?
Would it be negative cosine?
Negative cosine, good. Now this one needs the negative, plus c. It needs the negative, why? Well, if you don't put the negative, right, then the derivative of cosine of x is negative sine of x, but we have positive sine x here, right? So we need to kind of get rid of that negative, so we put a negative in front. So what I'm doing now is I'm trying to pull from your knowledge of derivatives from what we've already done. Like you know the derivative of sine is cosine, you know derivative of cosine is negative sine. So that's how I'm kind of building this. What other ones would I expect you to know here? I would expect you to know this. I would expect you to know the antiderivative of secant squared x, right, Josh?
It's tangent.
That's right.
Right.
It's tangent x plus c. The antiderivative of secant squared x is tangent x. Why? Because you learned in Cal 1, which you're still in Cal 1, you learned in Cal 1 that the derivative of tangent is secant squared, right? Now I skipped something here. I went from cosine, sine, I skipped something. I didn't do tangent, did I? I skipped tangent. All right, so maybe I forgot, right? What if little f of x is tangent x? Can you tell me what the antiderivative of that is? So think about what you know from your Cal 1 experience so far. Is there anything that you take the derivative of and get tangent?
I don't think there is. There
Yeah,
is.
we never did anything where you took its derivative and got tangent, did you? Did we? We never did. So what's the antiderivative of tangent?
Would it be an empty set?
No, there is an antiderivative. We just
Is
don't know it. We just don't know what it is.
Because it involves like undoing quotient rule, right?
It involves
Because-
undoing the quotient rule, exactly. Because you can look at sine or tangent x is sine x over cosine x. Now let me show you
that's
what it
worse.
is. Can I show you what it is? I'm going to show you what it is. It is natural log of, how do I want to do this? Yeah, I'll do it this way. Secant x. Natural log of the absolute value of secant x plus c. That's what it is. Now, look here, this, I'm not expecting you to know why. Okay, so let's not talk about why it's this. Let's check that it is. Can we check it? How do we check it? Take its derivative, right? What's the derivative of the natural log of something? Uh-oh.
It's
1 over x.
one.
Yeah, it's one over that something.
1 over the something, right? Chain rule times now the derivative of what's in here. What's the derivative of secant x? So you need going into Cal 2, of course you need to know what the derivative of sine and cosine and tangent are. Those you have to know. But there are 3 others and you need to be comfortable with them now. Like, get moving along. So you should know the derivative of secant x, or at least on your formula sheet know where it is. Has someone found it yet?
Secant x times tangent x.
It's secant x times tangent x. And you see what happens?
The C can cancel out and you just
Cancel and you get
end
tangent,
it with tangent.
right?
That's
Get tangent. So how in the world would we have come up with that on our own? Does that make sense? Like, that's a difficult
no.
thing to see happening. So stay tuned, okay? Stay tuned. You will learn this, not in this class, but well, you know what? There is a chance we may get to this. Stay tuned. We might touch this if we have chance, maybe a little bit tomorrow, next class. All right, we good? Understand? So just ignore this. This is just more to make you think, hey, there are certain things we can't do, but there are also things we should know how to do. The antiderivative is cosine, sine, secant squared. All right. How y'all feeling?
That was a crazy one.
Yeah. All right. So we need to establish some notation before we proceed any further. All right. We need to establish some new notation. This is terrible notation for me to write this down, ask you to find capital F. We need something new, all right? Something brand new that will help you understand that I want you to find the antiderivative of something, all right? So new notation. Here's what I'm going to do. If I want you to find the antiderivative of a function, this is what I'm going to write. I'm going to write this symbol. Okay, now this symbol, think of it as an S that's been stretched out. All right. It actually does stand for the letter S. All right, but that will come later. This symbol right here lets you know I want you to find me the antiderivative of something. All right. Now, what I want you to find the antiderivative of, I'm going to write right here. That's the function. I'll just place it right there next to that symbol. And that's going to tell you, hey, go find me the antiderivative. And then next to that, I'm going to put dx. Now, that is going to look very confusing to you initially. You're gonna be like, what the hell is that? Think of it this way. Okay, think of it this way. If I were to ask you to take the derivative of x squared, take the derivative, not antiderivative, the derivative, you would say 2x, right? And then that would take care of the power rule. Then you say times, now you do the derivative of x. This is chain rule, but what's the derivative of x? 1, right? That's 1. But it's there. It's a 1 in this case, right? It's a 1 in this case. But if for some reason we were differentiating with respect to a different variable, then it wouldn't be a 1. It would be something else, perhaps dy dt or dy dx or something like that. So this right here that we write next to it, this is called the differential. And I want you right now, because it will make more sense later in Cal 2. Right now, I want you to think of this as something that keeps track of the variable in the problem. So this is just letting me know, hey, look, I want to find the antiderivative of this function where I treat x like the variable. X is the variable, all right? This right here is the new notation we have. This symbol is called the integral. Integral, all right? And the function that you're plugging in, the function you're going to try and find the antiderivative of is called the integrand. Integrand. So what this symbol should produce should be the capital F of x plus some constant. This is your general antiderivative. So I know that's a lot to throw at you. Let me give you some examples so this doesn't look so weird.
Question.
Yes.
Are integrals antiderivatives?
Yes.
Okay, so if I was to take the integral of something, I would be taking the antiderivative.
Yes, but there's two types of integrals.
Oh,
there's
no.
what's called an indefinite integral, and there's what's called a definite integral. What we're looking at here is called an indefinite integral.
Okay.
Because our answer is a family of functions. It's an infinite number of answers. So we're not definitely sure what function it is, but it comes from this family.
Would the definite be something you learn in Cal 2?
Yes, the definite is going to actually represent something else. I don't want to give it away. So
Gotcha.
it will represent something completely different.
Spoilers.
Yep. I don't want to ruin it for your Cal 2 instructor. Okay, so here we go. Seeing this in action. If I write down now this. That's me basically telling you to find the antiderivative of x squared. And we've already done this, right? This was 1/3 x cubed plus c. Make sense? It's just new notation. That's all it is. If I write down this, All you're doing is looking at that and finding me the antiderivative. Sine x plus c. We're kind of not paying much attention to these things. In the yellow, we're just really looking at the function saying, what's its antiderivative, all right? There's another one. So what's the power on that x?
1/2.
1/2. So if we want the antiderivative, I'm going to add 1 to 1/2, which would be x to the 3/2, right? And then I put the reciprocal out front. We've done all these. That's why I'm not showing much detail, right? We've actually done all these antiderivatives earlier. All right. How are you feeling? Yeah, just new notation.
Yeah, just new notation.
That's all it is.
Yeah.
All right.
The thing that's
so-
been throwing me off the hardest is remember you put that plus C at the end of all of them.
Yeah, so I'll give you a little bit of a warning on that. Some professors are extremely rigid when it comes to the plus C. Like if you forget the plus C, it's wrong. All right. And then there's others that are more lenient. Like I'm lenient in the beginning. Like when you're first learning it, like you forget the plus C, okay, I'll take a point or two off. But if you forget the plus C later, it's, you know, more points off. Because you have to get used to that idea that there's always a plus C on an antiderivative. All right. Trying to think of what I want to do now. Yeah, let's do this. I'm not ready for the other thing. So do you remember this? Do you remember this? Recall that if d of t is a position function, in other words, this gives you the position of an object over time. Graphically, here's time, here's position, distance, let's say. Then the graph of this function looks like whatever it is, right? D of t. What was the derivative of this? What would the derivative of this function give you?
Velocity.
The derivative of that function would give you what we call the velocity function, right? Y'all remember me talking about this, right? Sharing this with you. Derivative of position is velocity.
And the second derivative is acceleration.
And then the second derivative is the acceleration function. Velocity and acceleration.
So then we could technically find it velocity with only our acceleration given.
Yeah, so the way we've learned this is that if we start with position, if we have a position function, we can take the derivative and we can get velocity. And then we take the derivative of that and we get the acceleration function. Now think about this. If you know the position function, right? If you start with this, that means you know exactly where an object is at every point in time. If that's what you're starting with, that's a lot of information to have. Every position of the object at every point in time. From that, we should be able to figure out the velocity at every point in time and acceleration. It seems like we should be able to, because that's a lot to know. Exactly where something it is at every point. We should be able to go and figure out the speed and then the acceleration. Now, this idea of antiderivative means that if we go the other direction with the antiderivative, right? We should be able to go from acceleration back to velocity, right? The problem though is this. What are we going to have when we do this? When we go antiderivative, what's going to be there?
C.
That plus C.
Exactly. We're going to have plus C. So we're gonna have a family of functions, aren't we? But if we could somehow figure out exactly what function it was, then we should be able to go back one more time and recover the position. But again, we're gonna have another family of functions. So I'd like to talk about that now a little bit. I want to actually see if we can't get a little deeper into this. So how many of you all have seen this or a version of this formula before? Okay, this is something you may have seen in physics or an algebra class, something similar to this. D of t equals -16 t squared plus v naught t plus d naught. Does that look familiar to anyone here? See a couple of
Yes,
people
I
nodding.
don't remember
Yeah.
what it is, but I think is that a kinematic equation?
It is. So, but yes, it is in physics. What this is basically a function that tells you where an object will be if you drop it on Earth. So if you're standing on Earth somewhere, like on a bridge, and you take a rock and you drop it, this formula will tell you how high it is off the ground after a certain amount of time. That's what this is. So the way it works is this. Let me point out some of the things here. D sub 0, this right here, this is always your starting height. And it's measured in feet. V sub 0 is your starting velocity. And that's measured in feet per second. Of course, t in the problem is time, and it's measured in seconds. And then the left side of the equation, d of t, is your height after t seconds.
So that's one of those, if you just drop it, that starting velocity is just going to be 0 and you
Yeah,
negate
so
that center portion. That's
let's say
for, I think.
Yeah, let's say we're standing on like some cliff, right? And we want to drop drop a rock off the cliff, right? Okay, we want to drop this rock and it's going to fall. So if we know how high it is, let's say it's a 400-foot cliff, right? Then that's what d sub 0 would be, all right? The only other thing we need to know to figure out the height of the rock at a certain point in time is its starting velocity. So if you just hold the rock out and let it go, then v sub 0 would be 0. If you take the rock and you actually throw it down, then you're going to give it a velocity, then v naught would be some negative number. And if you take the rock and throw it up first, then it has to go up and then back down, and that means v naught would be a positive number. That's not important right now, okay? I'm just trying to show you like what this formula does, all right? If you've seen it in the past, great. If you haven't, I'm trying to give you a general flavor for what it does. Once you have the formula for the specific rock we're talking about, then you can figure out anything you want. Like after 2 seconds, how high is it? You can figure out how long it takes to hit the ground. There's so many different things you can figure out about the rock once you have this set up. The question I have is, where does this come from? Where does that formula come from? Like, I know they give it to you in physics, but where does it come from, right? That's the question. So I'm gonna let you think about it for a moment and see if anyone can kind of think about all these ideas together and maybe figure out how this is generated. I'll be right back. Refill. I need some coffee, maybe. 2:15, too late for coffee. All right, y'all ready to talk about this? So I want you to think about, well, did anyone come up with an idea of how we might be able to come up with it?
So I had one thing, but when I actually did anything with it, it didn't seem to give me anything that I recognized. But we could just say that, hey, what if that D, like the D naught, is effectively being a C, and it's just an integral of another of another formula, but the other formula is just nothing.
All right. Does someone have any other ideas here?
I think it's an integral of velocity, because if you take the derivative of it, you lose distance. You're just measuring velocity in time.
Okay. Yeah, so I think you're starting to get there. Look, think of it this way. We have an object that's falling on Earth, right? So when you drop an object on Earth, all objects will fall at the same rate, regardless of their mass. Now that we have to get around that first, okay? So if I drop a bowling ball and I drop a piece of paper from a bridge, they will both fall together. But wait a minute, that's not what happens, right? The air actually slows the paper down. If you take the air away, though, if there's no air, the bowling ball and the piece of paper will fall and hit the ground at the exact same time. So that's the first thing you have to know going into this, that without air, okay, without air, all objects will fall on Earth at the same rate. Okay, that you have to be okay with to start this. And they ran an experiment when they got to the moon. When we went to the moon, if you believe we went to the moon, I hope you do. They took a hammer and a feather, and they did this on video, and they dropped the two and they both hit the ground at the same time. And they were just really proving what they already knew, but it was kind of like an FU to everyone who told them that that was crazy, because there's no atmosphere on the moon. So the feather and the hammer hit the ground at the same time. So if you take air out, all objects fall at the same rate. And they fall at the same rate because the acceleration of gravity is constant on the Earth. Well, on the surface. I mean, if you go to higher altitudes, the further away you get, it changes. But let's just say in general, like just generally speaking, the acceleration of gravity is constant. Does anyone know what the acceleration of gravity is?
9.8 meters per second
So
squared.
this is something a lot of people have heard of, right? So when it comes to gravity, the acceleration of gravity is negative 9.8 meters per second. A lot of students have heard that before. Now, what I'm going to do is I'm going to take that and I'm going to convert it from meters per second into feet per second, because we work with feet in the United States more than we work with meters. So I'm going to convert this. Now, I'm not going to do it. I already have it written down. It's about 32 feet per second. All right. That's the acceleration of gravity on the Earth. Okay.
That suddenly fits with that derivative I took.
Yeah. So now what I'm telling you is that this is the acceleration function on Earth. It's a constant, negative 32. I'm going to not do the feet per second, but that's the acceleration function for Earth. All right. That's it. Negative 32. It's constant. If I drop a ball from a bridge, or I drop a ball from a plane, or I drop a ball right here in the room, they all accelerate at the same rate. Okay, they all accelerate at the same rate because gravity is having the same effect on it, no matter where it is. So acceleration is constant. So if I know the acceleration function, I can find the velocity function. How? How do I find the velocity?
Antiderivative.
The antiderivative of this. So can you find me the antiderivative of negative 32? D, what variable should I use here? D what?
T.
T, right? Because T is my variable, right? T is time, dt. What is the antiderivative of negative 32?
T to the negative 32, or hold up. 1 second.
It would just be 32t, wouldn't it?
Negative
C?
32t.
Right.
Yeah,
Negative
plus C.
32t plus some constant. Do y'all follow that? The antiderivative of negative 32 is negative 32t plus a constant. Yes? Okay, so here's what I know. The velocity on Earth of an object dropped, right, is going to be negative 32t plus a constant. I don't know what the constant is though, right? I don't know what it is at all, right? But watch this. What would the velocity at 0 be? If I asked you to plug 0 in for t, what would you get?
0.
0 there, but wouldn't you still have plus c?
Yes.
So isn't c the velocity at 0? Isn't it? So let's call it,
Yeah.
let's call c, instead of v0, let's call it v sub 0, and everyone understands that that's the velocity at 0. So now what does my formula become? My velocity function is negative 32t plus v sub 0. Some constant that I don't know, but it is, whatever that constant is, it's the velocity at the beginning. Now what?
You would do the same
No,
thing.
integrate
Do
it
the
again.
same thing again. Let's do it over. Let's do the antiderivative of this, and that will give you position, right? So my position function, d of t, should be the antiderivative, the integral, of the velocity function, which is negative 32t plus v naught, all of that dt, just keeping track of what the variable is, equals, all right, what's the antiderivative of negative 32t?
Negative 16t squared.
Negative 16t squared. Now, how are we getting that? The negative 32 comes for the ride. The antiderivative of t by itself is 1/2 t squared. And so the half and 32 kill each other off, and you just get the negative 16 t squared plus, okay, careful. What's the antiderivative of v naught?
V naught t.
V naught t, because v naught is just a number, right? It's just some number. So the antiderivative of that should be v naught t. And then plus, because we did an antiderivative, some constant c, right? Let's not call it c, let's call it d, because I don't want us to confuse it with the c we found up here. I'm gonna call it some other constant, d. With me? There's one more thing I know. D at 0, what happens at the beginning, at 0 time? If we plug 0 in here, we get negative 16, 0 squared, plus v naught times 0, plus d. So d, right, the constant is actually the position at the beginning, the position at 0, isn't it? D must be my initial position. We'll call it d sub 0. And so what we have is this becomes negative 16 t squared plus v naught t plus d naught, which is the formula that I presented in the beginning of this problem as our position function for an object falling on Earth. Without air, you have to take air out. If you want to add air, it gets more complicated, all right? But this is it without air. If we want air, it'll get more complicated. That's okay. I mean, that's the way math works. We're trying to model the world. So we start basic and then we start adding things into it. Like if you've ever studied free body diagrams in physics about like an object and you're trying to pull it or, you know, move it or something, you always take out friction first. You act like there's no friction. And then later on you add friction in. So, you know, you always start basic. So that's pretty awesome, huh? I mean, that's the formula, right? What did we need to actually create that formula? What was the only thing we needed?
Gravity.
Gravity, that's it. Which means if you go to the moon and figure out what the acceleration of the gravity is on the moon, I can give you a different function that would give you, if you drop something on the moon, I would be able to produce a formula for where that object would be on the moon. And guess what? It's going to be a quadratic function. It doesn't matter what planet you're on. If you know, as long as the acceleration of gravity is constant, your position function will always be a quadratic function, no matter what, because you start with a constant. Antiderivative once takes you to a linear function. Antiderivative twice takes you to a quadratic. Understand? And that's just the way the universe works, okay? I mean, it's just the way it is, all right? So it's pretty cool. I always look at it this way. That -16 is because we're on Earth. If that number changes, we're on a different planet. Okay. We have 12 minutes. Here's what I'd like to do in the last 12 minutes. I'd like for us to try something harder. Now, this may seem like all of a sudden I've turned up the heat quite a bit here. I would like to know what the antiderivative of this is. 2x times cosine of x squared. So let's just take care of a few things first. We have product here, right? So if we're going to do the antiderivative, we cannot just look at these separately. Okay, so I can't just say, hey, what's the antiderivative of 2x? Go find that, and then find the antiderivative of this, and then write that down. I can't do that because it's a product. If it was addition, subtraction, I could do them separately. But because it's product, I can't. Go ahead.
Would this be a chain rule that occurred here?
It looks like maybe. What chain rule do you see? I mean,
it looks like it was probably sine of x squared, and then you make that cosine of x squared times 2x.
You're saying you think that the antiderivative of this is this? Or more?
Yeah, plus c.
Yeah, this?
Yeah, I think so. Would that be, is that correct?
I don't know. You tell me. Y'all tell me. Is that correct or not?
That looks right to me.
Looks it.
Yeah. Yeah, it looks
When you
right
take
to
the
me.
derivative of this, right? You start with this is a chain rule. The derivative of this would be cosine of x squared, right? First, and then times the derivative of what's inside, which would be 2x.
Yeah, 2x.
That's
And the c goes
exactly
away.
this, right? That's exactly what's here. Now, Hunter saw this, right? Hunter saw that connection. I can't teach that, okay? I can't teach that ability to see a connection like that. I can't. That's what makes Cal 2 extremely tough, all right? But I do, there is hope here. There is something we could do though that will help, all right? If you can see this, great. If you don't, and look, I mean, this problem is very easy for what we're headed towards, but let's act like we don't see that, okay? Let's just act like we don't see it. So the first technique to try and find antiderivatives, other than the rule I already gave you, power rule, the first technique that we learn is something called substitution. Substitution. That's the first technique. There's actually several techniques, all right, in Cal 2. Substitution is the first one. Then something called integration by parts. Then something called trig integrals. And then another thing called trigonometric substitution. And then a last thing called partial fraction decomposition. Those are the 5 kind of like tools you have in your toolbox. You know, it's like sometimes you need a saw, sometimes you need a drill, sometimes you need a hammer. In Cal 2, you have 5 tools, all right? And it's up to you to figure out which tool you need for which problem. And that's hard. It's harder than the product rule, chain rule, quotient rule. Those are easier to identify. When you look at something, right, in Cal 1, when you look, it's easy to see a product. It's easy to see a quotient. This is harder. How do we do substitution? So let me show it to you first, and then I'll try and formalize it. I only have 8 minutes. So the way substitution works is this. You look at your integral, you look at the integrand, okay? So I'm focusing my attention on this. And I'm gonna make a substitution, which means I'm gonna replace something in the problem with something, all right? But I have to figure out what. So what I'm looking for in here is this, two things. I'm looking for something, okay? So I wanna first look for something I'm gonna call something. I don't know, I don't even know what it is. It depends on the problem. But I'm looking for something in there. Okay, so I'm searching, and I got to see this something. And then I also need, to see the derivative of that something. So I'm looking in here, and I'm looking for something, and I need to see its derivative also there with somewhere in here. All right. Now there's a few little asterisks I'm going to have to add to this, but for now, this problem, first one, I think it's easy. X squared is the something, right? Everyone see that x squared? That's the something, and its derivative is 2x. Yes? This is the something. And this is the derivative of the something. Once you've identified that, then you're going to make your substitution. You're going to let u be equal to the something. Okay, so I'm going to take the something that I found, not its derivative, but the something that I found, I'm going to take it, I'm going to call it u. All right, I'm making a substitution. And now what I'm going to do is I'm going to differentiate both sides of this equation with respect to x. So I'm going to take du dx equals 2x. Right? One more thing. I'm going to multiply both sides of the equation by dx. So on this right here, on this equation, right here, I'm multiplying both sides by dx to clear the fraction on the left. Y'all got it? Now what I'm going to do is I'm going to take this original integral and I'm going to rewrite it. So first thing I'm going to do is reorder things, just kind of switch things around. I'm going to put the 2x in the back with the dx. So I took that 2x there and I slid it to the back. And now we're just going to play a game of matching. Okay, we're going to play this little matching game. I've got a 2x dx here. You see that right there, 2x dx. I'm going to replace that with du. And then I see an x squared here, I'm going to replace that with u. And then just rewrite the whole problem. So when I rewrite it, I get what? Cosine
u
times cosine of u, right? Cosine of u, and then times what's the 2x dx become?
du.
And now this is an easier problem to do, isn't it? This is saying what's the antiderivative of cosine of u? And so you need to know, okay, oh, the antiderivative of cosine of u, well, that's just sine of u, isn't it? Plus a constant that I don't know. And now you do a back substitution and you replace your u with what it was. What was u? X squared, right? So you get sine of x squared plus c, which is the answer. You can always check your work. That's one good thing in Cal 2. You can always check your answer because you can just take the derivative and it better get back what you started with. Let me give you another one just to get you set up. I don't think we'll have time to do it. How about this one? Let me think for a second here. Yeah, how about this? How about 5x cubed over 1 plus x to the 4th dx? I want the antiderivative of that. So very quickly, we've gone to some much more challenging problems, haven't we? I mean, look at this. Keep in mind, if it were flipped the other way around, right? If this denominator was on top and the 5x cubed was on the bottom, I would split it into 2 fractions and just use the power rule from what we did earlier. If it were the other way around, but it's not. So I'm not going to waste your time. This won't go any other way other than substitution. So you need to figure out what's the something and what's the derivative. Now, do you remember me telling you that there's a couple little asterisks on here that I didn't put? Here's the thing about this derivative. Okay, the derivative that you're looking for, right? Because you're trying to look at and see something and its derivative. That derivative, it's okay to be off by a constant. All right, so you know, like on this problem, we picked x squared and the derivative was 2x. It would have been okay if this was just an x here, not 2x, because then we would have only been off by 2. All right, that's a constant, we're off by 2, that's okay. If this would have been 10x, it would have been fine also. It's okay to be off by a constant. You just can't be off by more than a constant. So over here, does anyone see the u?
That means that u is x to the 4th.
You could let u be x to the 4th. What's the derivative of that? So if you take the derivative of that, what do you get?
4x to the 3rd.
4x to the 3rd, right? And you have a 5x to the 3rd, don't you? On top there. So you're off by a constant. You have a 4x cubed, there's a 5x cubed there, you're off by a constant. That's okay. All right, that's okay. Now, hold on, don't get too far ahead of me. This is not the best choice for you. There's a better one. It's close, but there's.
Is it 1 plus x to the 4th?
Why not the whole thing? 1 plus x to the 4th.
Because then we can just kill 1 entirely.
When we differentiate, the 1 won't make a difference with the derivative, will it? Du over dx will still be 4x cubed dx, right? That'll still be the same. Hey, we're out of time. We're out of time. I don't feel like finishing this because I want you to maybe think about it yourself. We've got, this is the substitution. This is what you do. Oh, I forgot to, I needed to do this on the next step. Sorry. I'm going to see maybe if you can figure that out. I'll come back next time. Next class, what we're going to do is maybe spend the first 20 minutes, 30 minutes doing more of the substitution, because I want you to see it on a couple of examples. And it will be on the final. I will put substitution on there. So we need to do some more. And then after that, I really just want to be able to talk about the final. So that means like come with questions, come with like anything you feel like you need me to address, okay? And if y'all don't have questions, I'm just going to keep doing substitution problems until we run out of time.
So I'm not bringing any questions.
Yeah. Yeah, these substitution problems, you know, it's the Cal 2 builds on itself. I mean, kind of like it has in Cal 1, but it's even more important in Cal 2. Like I told you, there's 5 methods, right? 5 tools. This is the first one. The second method, you can't do it. If you don't know how to do the first method, you can't do the second. So like you have, they just build on each other very quickly. All right, everyone, have a good day. I will be here, see you on Thursday for our last meeting.
Can I ask you a question unrelated to anything we just talked about?
Yeah, I'm gonna stop the recording and I'll hang out here for a few minutes. Let me check something though. Give me a moment.